Welcome. Good afternoon, everyone. Welcome to this first data science meetup of 2021. We are very happy to have you all here and have you all watching. Maybe let's start introducing ourselves. Max on my left or right side, and my name is Jessie. We will be your host for today. So hopefully we will we will have a full meetup full of interesting knowledge to share. So we are very excited. So I would say let's not wait any longer and start with our first talk.
Yes, welcome everyone. You see there are 3 talks. The first 2 talks have an active learning component in them. So the first presentation is by Anil Panda. Anil is a senior data scientist in the risk and pricing advanced analytics team. He's been there for 5 years and has a background in IT. And his presentation is about solving a cold start problem for NLP with active learning. So Anil, take it away.
Hey, thanks, Max. Thanks, Jesse. Good afternoon, everyone, and I hope you are doing well wherever you are. Before I start, I would like to say thanks to Jesse, Max, and Daniele, and the entire team of ING Analytics for providing me this opportunity to present my learnings and my talks here. Today, we are going to look at active learning and how we used it in a real life problem to solve an NLP use case. All right. My name is Anil. I'm a data scientist with Risk and Pricing Advanced Analytics, where we create financial, non-financial risk models and also pricing advanced analytics models. Right. So let's begin. Hopefully you get some knowledge out of this session. For today's agenda, what we are going to do is we're going to look at ARIA. So we're going to talk about a use case where we used active learning and how it came to our rescue. We're going to look at active learning in general. What does it mean? What is it about? We'll talk about the different sampling techniques that we used, some of the learnings and some of the best practices that we got from active learning, also deploying active learning into our projects. We'll also look at some of the Python implementations, also look at our own implementation that we did, and finally we'll look at the results. So let's begin. So before we start, what is active learning? Let's look at what is ARIA, right? So ARIA is an early warning system that we have within ING for the risk managers of wholesale banking. So wholesale banking is, let's say, a department within ING which deals with companies and those kind of things, right? So they have an early warning system, and then you have risk managers within wholesale banking. Now, as a risk manager, you are managing different companies, and these companies are in your portfolio, and you would be interested to see if there are any sort of, let's say, early warning systems that you can look for these companies, and you would like to know what's happening within the companies companies in your portfolio. So for that, there's a tool called as ARIA, and it has a lot of components, but let's talk specifically about some of the components or some of the machine learning models that we have within ARIA. So within ARIA, what we do is that you have different news items, public news, and we take and we try to create signals with respect to mergers and acquisitions, with respect to fraud, with respect to bankruptcies, sanctions, environment and climate change, and human rights. So I've marked the bottom 2 in green because that is where we use active learning to create, let's say, some of the solutions that we wanted to have a look. Right. So to summarize, ARIA is an early warning system which is used by risk managers to manage the companies in their own portfolios. Converting this into, let's say, a machine learning problem is what we have here is that basically, given a news item, we try to predict if it's about, for example, human rights or not, right? So it's a binary classification problem that we are talking about. So, right, so if it's a binary classification problem, let's say the way to create a model is pretty simple, right? So you have a data set with your labeled data, you train a classifier on top of it. Since it's an NLP problem, you do all the required pre-processing, the tokenization and those kind of things, and then you create a simple machine learning model. However, the problem that we had with this particular use case is that the training data or the labeled training data that was available to us was not fit for purpose. What do I mean by that? Is that the label data, the risk managers are interested in specifically negative news about the companies in their portfolio, because that would signal some sort of an early warning signal that they would like to monitor or they would like to talk to with their clients. So on the left hand side, what you can see here is that it's a news item that the risk manager would be interested to know about, right? So if it's a risk manager who's managing, let's say, uh, PNB Paribas as a company, and then you would say, okay, like, okay, this is something that I need to be aware of. But on my right hand side, you see this is a news still about human rights, but maybe it's not that interesting to a risk manager, since he is not dealing with the entities mentioned here, but then he is dealing with the entities mentioned here, right? But then the data set that we had, or the training data that we had a label of human rights for both of them, and that's something which we did not want, because if we created a machine learning model using the, let's say, the pre-labeled data set, we would get a lot of false positives, and that's not something the risk managers would want to see. They want accurate information and not, let's say, false positive use cases. Another challenge that we had is that also, and luckily, human rights and environmental news is quite rare information to find. That has let's say, bearing on some of the sampling techniques we use later, but then I'll come to that point sometimes back, right? So to summarize this slide, we had pre-labeled data set, but that was not fit for use, so we could not use them. So we had to come up with our own technique to create our own labeled data set, and that is where active learning came to our rescue. So what's active learning? So the definition of active learning is that it's a special case of machine learning in which an algorithm can interactively query a user or an oracle to label new data points. So that's the definition, but how it works is that it's actually pretty simple to see. So you have an unlabeled pool of data set. You use some querying or some selection techniques to query data from this unlabeled pool. You give them to a human annotator. The human annotator labels those data sets with his own knowledge. That is used to create a classifier, and then the circle completes again and again. So this simple method is quite useful in let's say, creating data set for your machine learning models, but also quite useful in cases where you don't have any labeled data set. In our case, for example, and then you can start and create your own labeled data set and create a model, right? One of the things that you would notice here is that, okay, the most interesting thing here is how do we select these queries? And I think that's, let's say, the crux of what active learning tries to solve, and then what we are going to look at today as well. So if you have an unlabeled data set, what is the, let's say, the most easiest thing to do is to do a random query, right? So you randomly query some of the points from the data set, you give them to a human annotator or an oracle as it is known in this case, and then you query as label 1 or label 0. Let's consider that for our problem, we only have a binary classification problem. So we are talking about either class 1 or class 0, right? So that is a random query sampling technique. The advantage that it's a baseline. So I think this is, let's say, the most brute force thing that you can do. It's a good starting point. And if in the future you create your own sampling technique and you are able to beat this random query, then that means your technique has some promise. But if you're not able to beat, let's say, random query, then maybe the technique is not that good. So that's random query. But again, here you're not using any information either from the data or from the classifier. So the next technique that we're going to look is decision rules. What decision rules do is that, for example, let's say you know that some features in your unlabeled pool can be more relevant to class 1. In our case, we are talking about news items. So for news items, we do know that, okay, if I'm looking at environmental cases, maybe I'm looking at companies which are involved in oil spills, or maybe companies which are involved in some sort of pollution. So these are certain keywords which can help me identify certain news items to sample, but then they may not capture the entire landscape of the problem that I'm trying to solve. They are high precision, but at the same time, I would get a lot of false positives if I just use decision rules, right? and obviously they're not as good as a machine learning model, so I need to improve on that. But then decision rules based sampling is a good technique to begin with as well. The third sampling technique in the baseline technique is a clustering homogeneity, and as you can imagine, it's quite simple as well. You cluster your data set, and then, for example, on the right hand side, you can see that I have three clusters, and then I can pick some of the points from, let's say, the green cluster here and label them, from the red cluster here and label them, and from the blue cluster here and label them. And if I find out that for the cluster red, I have, let's say, 90% class 1 and 10% class 0, I can, for example, mark all of them to be class 1 and then create some sort of a data set to start working on further. So here, so these are, let's say, some of the very baseline techniques that you can start with, but then you are not using any sort of information either from the classifier, and then that's something that's a waste, right? So maybe let's look at some more complex sampling techniques that make use of this information from the classifier. So the first thing, or let's say the one of the most uh, popular sampling techniques is called as uncertainty sampling. And the idea here is very simple, right? So once you have a small data set to create a classifier, you can use that to label or to predict the outcome of that classifier on your entire unlabeled pool, and then you choose the points to be labeled by a human annotator which are on the boundary of the classifier, or for which your classifier is the most uncertain about. For example, let's say again a binary classification problem, and then for a particular data point, your classifier says there is a 0.9 probability of it belonging to class 0 and 0.1 probability of it belonging to class 1. Now, if you see the difference in probabilities, it's like around 1 minus the difference. So it's like 0.1. So the uncertainty is quite low because your classifier is very sure that this data point belongs to class 0. But that's not what you want, right? So you want a point in which, let's say, the probability of class 1 given by the classifier is 0.51 and the probability of class 0 is 0.49. And here you see 1 minus the highest probability is 0.49. And then they would say, okay, so my classifier is not really sure, maybe a human intervention or a human annotation could work there. So that's something that you can do here and say, okay, like, give those points to a human annotator, and he or she can, let's say, label it either class 1 or class 0. There are other variations as well as the margin classifier and the entropy selection, but which work more or less in similar ways. Now, what are the cons of this technique is that you need some sort of a data set to train a classifier. Even if a rudimentary one, you need some sort of a labeled data set to begin with. You can get stuck in the localized region of the decision boundary because your classifier would only predict, or let's say only give you points close to the decision boundary here. So if you look at this example, so it can get stuck here, but then you can use different classifiers to get through that problem. One of the, let's say, more cons, or one of the more challenging things here is that this is very prone to, or it detects outliers more often than not. For example, if you look at the use case or the things that I mentioned here, you want to distinguish between two class, a green class and a red class. And what most of the time with uncertainty sampling you would get is a point A, which is exactly on the decision boundary. So this line is a decision boundary, and you would get a point here, which is okay. But then I think it would have been more useful if we get a point for sampling, for example, point B, which would change my decision boundary and get me some more information. So that's one of the inherent challenges or inherent disadvantages of uncertainty sampling. We can obviously solve that by using something called as a a query by committee or a query based sampling techniques, right? Again, the idea here is pretty simple and intuitive. What you can do is, instead of training one classifier, you can train multiple classifiers, right? All of them are decision boundaries and they explore different regions of your problem space. Once you do that, and then you can have some sort of a voting mechanism to say that, hey, this classifier, like if you have a query of three classifiers, you can say, okay, like give me the points on which my classifiers disagree the most. Give me the points on which my classifiers, maybe two of them agree, one of them disagree. right? So you can also do that sort of an implementation, and that's a simple query-based classification, or a query-based query by committee sampling technique. You also have more complex sampling techniques, but for our problem, to solve the problem that I mentioned before, we did not use those complex one, because these, let's say, simple classifier or simple sampling techniques did solve our problem. But just to give you an idea of what those complex sampling techniques are, so one thing is called as your expected model change, in which you say, okay, give me the points for labeling. If I knew the label for those points, my model would change the most, right? So that's expected model change. And also what you can also have is called as the expected error reduction, in which you say that, okay, select an instance that would reduce the generalization error the most, for example, right? So you have multiple sampling techniques that you can use to solve this problem. But again, which algorithm to use? So if you're starting out with a problem, which algorithm to start with? And I think the answer depends, right? So if you have some knowledge about your data set, some knowledge about your class distributions, you can either start with a query-based sampling or a decision rule-based sampling, or you can also start with random sampling when there is no data set available. And once you have some more data set available, you can, let's say, for example, change to a more sophisticated technique like uncertainty sampling of that sort. So as you can see here, if you just go with random sampling, your performance would take a lot more time. So you have to label, for example, here 20,000 samples to reach the same performance. But if you switch somewhere after labeling a few samples, then you can reach the same performance easily using a query based sampling, or some sort of an uncertainty sampling. Or I think the best thing is to combine different approaches, and I think that works the best in my opinion. Right? Okay, so we have covered what is active learning now, what are the different sampling techniques what we can use, and also what and how we can use those different sampling techniques to achieve our performance. Again, the point is, okay, and then when do we stop, right? I think in this entire domain of active learning, a simple thing is cost, because labeling news items costs either money or time, depending on the problem statement. If it's an NLP problem, maybe it's an easier one to solve. But if it's an image classification problem, still easy if it's a normal image or like a very simple image. But if it is things like X-rays and those kind of medical images, then your cost and time will be very high. And you can decide upfront, okay, let's say I'm gonna spend, I don't know, 2-3 hours, or maybe I'm gonna set $5,000 for different annotators to solve to label and give me certain points, right? So cost and time is a point. After, you can also stop when you have some sort of a convergence, that you notice that your human annotators notice some sort of a convergence. What is this chart? I'll come to that later during the results. But then essentially what I want to show is that, as you see, after this point, the performance is not increasing much, even if you're labeling more points, right? So you can see, okay, maybe for this problem statement, I've covered my class enough and my performance is not increasing that much. So let me just stop labeling and see what performance I've reached. Or you can have some sort of a stopping criteria, and you say, okay, if my precision reaches this number, my recall reaches this number, or my AUC is about zero point 0.8, for example, then I stop, right? So this can be some of the, let's say, the stopping criteria that you can use for your own problem, right? So as I mentioned before, these are the simple different sampling techniques, and also what are some of the Python implementations that you can use in your problems, or to solve your problem when you don't have a labeled data set and you want to use active learning. So one of the, let's say, the more famous packages is called as Modal, and I think it is compatible with sklearn. You can use an sklearn model. It has an API which is similar to sklearn. It is actively maintained, and it has good tutorial and documentation as well. Similarly, you have other libraries as well, but with some adaptations, or let's say they are not following the sklearn API, but at the same time, you can still use them depending on the problem that you have. Right. So, for example, if you were to use Modal, I think that it's a simple one. You give a classifier, that like a sklearn classifier you want to use. You give your training and give your X and Y data sets, and then you can start working with Modal. However, what we have also noticed is that it's quite simple to implement at least the basic sampling techniques. Sorry again, I think if the points here are not very visible, but then maybe when you have the slides, you can look at the code properly. But then I think, like I said, it's quite simple. You can see, okay, 1 minus your Back's probability, that's your uncertainty. You can calculate entropy with some of the SciPy functions that you have. And then if you want to use query based, you can define your own function where instead of using one classifier, you use multiple classifier. You can also use a random method with simple random selection using indexes. And then you can select, okay, how many points do you want to label at once? And what we chose in our problem is to do our own implementation rather than use any of the scikit-learn or any of the Python implementations available before, right? And it's quite easy to do as well. So coming back to our problem, and like I said, I think so one of the problems that we had is that we had an unlabeled data set, and we want to come up with a data set for training a machine learning model where we exactly want only the negative news items and not the positive ones, so that we don't have a lot of false positives in the news. So what we did is that we labeled about 1K news items for environmental model, about 200K or 2K for human rights. And then we used a combination of query or sampling methods, uncertainty sampling, query-based sampling, but also decision-based sampling to come up with the first set of, let's say, points so that we can use any of these complex, complex sampling techniques. So there is a team within ING which is called as an ESR team. I think they helped us with coming up with the initial set of rules as well, and all the model and all the, let's say, the human annotation was done in collaboration with them. Uh, a simple logistic regression plus a TF-IDF NLP model works the best, at least in our use case. It worked as well. The data set that we created using the active learning technique, it met the predefined KPIs, and also the model explainability results that we obtained after creating the models, and those were also in line with the expectations, what you would imagine or what you would imagine from such a machine learning model to do. On the right hand side, what you can see here is the progress of your target or your AUC that you want to measure. And you can see that as we labeled more and more points, our performance on our test set increased. And at some point, it starts to, let's say, slow down, and it does not improve anymore. So that's where we said, okay, like, I think we have reached the convergence here. So let's stop. And I think that's quite interesting to see that as you label more points, your performance increases, and that's something interesting to see as well. These models are already in production, which were put to production last year, and they are being continuously monitored to see model performance and drop, and then will be updated periodically uh, uh, in the system as well. Right. So here you can see that, okay, when you don't have a labeled data set, how you can use active learning and very simple sampling techniques to come up with a data set to create a machine learning model which you can actually use. And as you use this machine learning model, you would get more data set, and again you can continuously keep on improving your model. And I think that's the most, let's say, uh, most important learning that you can take here, is that even if you don't have a labeled data set, but you have some sort of knowledge and some way you can create a label data set, put in some time there, and then you would have a good enough data set to use all of these sampling techniques, use all of the active learning techniques, maybe more complex one depending on your problem, and then you can come up with a good model that you can use. Right. So to conclude, I think yes, you can use active learning if you have a huge label of unlabeled data set, and but you have some humans to provide you the ground truth. There is no best query algorithm as such, but still you can start with random sampling and then switch to some sort of an uncertainty based sampling on what we call as the elbow technique. Again, no best way to measure convergence, but then I think the best way is to uh, put in mind and say, okay, these are the costs, this is the time that I want to put, and then you can decide if you have reached your KPIs or not. Some of the problems to consider are obviously humans or any sort of annotators are not unnoisy, and the cost and the speed of the annotation as well, right? So that's it. Let's say from the presentation today, you can reach out, you can scan the barcode and reach out to me on LinkedIn if you have more questions and or any sort of other questions as well. If there are any questions, I think we have a few minutes to answer them.
Can you hear me? Yeah, thanks for the nice presentation, nice overview. So we asked people to, if you have questions, post them in the chats. There is one. I also have a few questions.
Yeah.
Maybe because I'm a co-host, I can ask my own question first. I was wondering about, you said you're using news sources.
Yes.
External sources that provide the news articles for you. So I was wondering about because typically they provide tags as well with the articles. Did you have those? Did you use those? What about? I'm just curious about that.
Yes, exactly. So I think so when we wanted to train the machine learning model, we had the tags, but as I mentioned, the tags were pretty generic, right? So for a news item which is negative as well as a general news item, both were tagged with, for example, human rights. And then the challenge there is that if you use that as your class 1, you would train a model which would give you a generic news as well as negative news, and then that would create a lot of false positives, because the requirement there is that as a risk manager, you have very less time and you only want to look at negative news about the company portfolio.
So the tags that were
that's
there,
why we could,
they were too unreliable, essentially.
yeah, they were too unreliable, and we need to come up with our own ways of doing it.
Let me ask a question from Nikki. Very interesting talk, well explained. And she asks, do you have an idea how many hours you saved by labeling fewer records because of the active learning that you implemented?
Right, because I think the main advantage of using active learning is that quite fast you can label, for example, 2,000 records, and I think we were able to do that maybe in a day or so, like setting up and everything. The challenge with using some sort of a random labeling technique is that the news items, for example, the environmental news or the human rights news, are quite rare, right? And thankfully they are quite rare, because if you look, if you have 100,000 records and you have to label each of them, or even if you randomly sample 10,000 of them, the chances of you getting a human rights issue is quite rare. So that's why we have to use the active learning technique, and then we could label 2,000 news items in a shorter duration of time.
Okay, cool. Are there any more questions, or? I see nothing. So I do want to say that actually there's a project in my own tribe that's kind of similar. So I think it would be very nice to bring you into contact. We're also looking at news sources, but it sounds like you're ahead.
Yeah, I think that would be pretty cool. Thanks, Max.
Cool. Thanks, Neil. Okay, cool. Then we can go on to the next talk. I think Jessie, you're taking over.
Yes, thanks. Thanks a lot, Anil, for your talk. So we have our second speaker, and that will be Samantha Michel. Samantha was an intern in the Wholesale Banking Advanced Analytics Data Science team. And she joined the team last March as a student to conduct research for her master's degree in artificial intelligence. Now that she's graduated and finished up her internship, she's working on a paper with her team based on a research project. Well, in her free time, she likes photography and she likes to travel. So hopefully for you, we can do it soon again. And today, with her talk, she will talk about active WSUL, improving weak supervision with active learning. So welcome, Samantha, and the floor is yours.
Thanks, Jessie. There's my screen. Yeah, thanks. I'll be talking about, indeed, active WSUL, improving weak supervision with active learning. So yeah, another talk about active learning, but it's going to be a bit of a different perspective. And yeah, I will be showing what we've been working on for this research project and this paper. So yeah, I've been working on this with a great team, Rafa, Luis, Max as well, who's here, and Nana. So yeah. First about the context. So if you want to use supervised machine learning for a problem, you're going to need labeled data, and usually you need quite a lot of it. And yeah, mostly in recent years, a lot of efforts have been going into obtaining these huge data sets, such as ImageNet, that have enabled the development of bigger and more complex discriminative models. But what we saw in the previous talk as well, it can be quite difficult in many projects and applications to get enough labeled data, because quite often you need an expert in the domain to provide the labels accurately, and there can be quite privacy constraints, and yeah, it can just take a lot of time. So for this reason, yeah, it's really good to consider how to make the most efficient use of our domain experts, so that we can turn this unsupervised problem that you might have into a supervised problem. And yeah, there's a few options. Active learning, like in the previous talk, where we try to determine which part of the data would be most useful to get labeled. Or another option is to try and create sort of less precise labels that may not always be accurate, but they're really much faster to get for a larger part of the data. So yeah, then I'm talking about weak supervision. So I'll go a bit more into how that would work. And to do that, I will be using a very simple data example where we have these unlabeled data points. And actually the ground truth is also here, but we want to try and get labels using weak supervision. So to do that, we start by asking our experts to define a set of labeling functions. And these labeling functions, in this case, they sort of, based on some value of one of the features, divide up the input space so that they assign one class to one side and the other class on the other side. In this way, we try and collect a few different sort of rules that, based on the knowledge of the expert, encode how the data can be roughly labeled. So these labels will be less precise, but in one go, they provide labels for all of the data. But yeah, then once we have those, we basically have these different weak labels that are sort of contradicting, because they in different regions they may agree or disagree. So the next step is to try and learn how they can be combined such that we get one label. And yeah, we then learn how to combine them in using this generative model that essentially introduces this this latent, this true label that we actually can't observe. So by learning this model, we are able to get probabilistic labels that are essentially distributions of this true label conditioned on the different values of the weak labels that were given. Yeah, I can't really go much more into how this model is learned, but it's from this paper here. So if you're interested in learning more, I recommend reading that. But now that we have learned to combine these weak labels into one probabilistic labels for our data points, we can actually train a discriminative model that uses those labels as supervision. So that was our goal. And this is also where we basically encountered a problem, because as you can see, with the labels that we obtained through weak supervision, we get this discriminative model with a decision boundary that is not really very accurate. Like, it doesn't really separate these classes well. And that is because what we find here in the labels, basically it can be because the generative model struggles to learn how to accurately combine these weak labels in a good way. So yeah, there are just some errors in these labels that then propagate to the discriminative model. So this is the problem that we want to address. And we do that by introducing some additional expert knowledge. And yeah, the approach that we took was to using an active learning approach, determine which data points would be useful to label individually, so that we can try and improve these labels. So we start with our generative model, like a part of the pipeline where we learn the generative model and get the resulting probabilistic labels. And then the first step, like in active learning, is to sample a data point using some sort of strategy. So let's say we sample this point, and then we ask our expert what the true label should be. So say the expert said true label is 1. And then to close the cycle, we want to use this true label to learn how to recombine these different weak labels or labeling functions into a better model, so that we improve our probabilistic labels. So that's the general idea of how we sort of combine this framework of weak supervision with active learning. And I'll first show what the result is will be in our simple example. So starting with our end results that I showed, where we have this rotated decision boundary. After some number of active learning iterations, where every iteration we add the label for one data point, we find that we are able to adjust some of these probabilistic labels that are given by the generative model, so that we can learn a better discriminative model. So using those few data points where we get additional feedback from our experts, we can fix this problem where we're basically not able to accurately combine the labeling functions that we have defined. So now we want to look at how many data points do we need to label to get this better results, and how does this compare to other approaches that we could take. So to do that, we first look at the synthetic data, or like a larger sample, just a larger sample of this example that I've been showing. And we look at what happens with the performance for the first 30 iterations, where every iteration we have 1 point for both the generative model So that's just the performance that we get if we take the most likely class as given by the probabilistic labels, as well as the discriminative model that was given by the decision boundary. And we'll look at the left two plots first. Now we start with this baseline for weak supervision, which just stays the same because we're not adding any label points. So this is the performance that we start with. These first two images at the top. And with our method that I just showed, that's adds active learning, which we call active result, the dark blue line. We start from this initial weak supervision performance, and quickly, as we start adding label points, we're able to improve the performance of both models to essentially the optimal level that we can get within only a few points. So yeah, that's a quite big improvement compared to just weak supervision. But then for active learning, of course, we don't start out with this initial information that we get from weak supervision, which we have in active result, this cycle. So active learning needs some time to catch up, but then really quite quickly also reaches this optimal performance level, because of course it's a quite relatively simple problem. So the difference really lies in here at the start, where our active result method has this advantage of starting with the information from the labeling functions. And finally, we have another approach we can compare to, which is basically like a competing approach from a different paper, because they also combine active learning with weak supervision. But apart from that, their approach is quite different. And what we see there for this problem is that because our performance really improves quite quickly, in the first iterations for this approach, we can't really see much improvement yet. So therefore, here on the right, we extend these discriminative model results to way more iterations. So we add up to 1,000 points out of the whole data set. And here we see that it slowly increases performance. But still, at the end, we're not even close to what we get here very quickly. So yeah, it does provide an advantage because we need way less data points that need to be labeled. Now, apart from synthetic data, we also tested this method on a few real data sets. So first on the left, for a spam detection task, we compare the active result method to the same kind of baselines. And again, we find that really quite quickly, compared to weak supervision by itself, the orange line, we're able to improve the performance within only a few labeled points. Again, at some point, active learning by itself also catches up to reach the same performance. And the competing approach does a little bit better, but yeah, again, needs more labels to reach a good performance. Now, for a different data set, an image task, it looks a bit different, because first here at the start, we see that with weak supervision, so the orange line, we start quite a lot lower. So we're not doing that well in the beginning. So therefore, it's especially useful to try and improve this performance. And we see that it works here as well. So within approximately 15 labeled data points, the active reason methods sort of improves the performance quite a lot. But then comparing to active learning, it's a bit slower again. But eventually active learning by itself, so without any weak supervision, overtakes these methods. So that's quite interesting, because it shows that because of how we combine active learning with our fixed weak supervision setting, so we rely on the labeling functions that we have defined, there can be a limit to how much we can improve the performance. So at some point, if we have a large labeling budget, it might just be a better idea to just use active learning, because we're not limited to what we how we define the labeling functions. So in all of these examples, we've seen that this combination of active learning with weak supervision is really very useful if the labeling budget is really very limited, so you can only label a few points. Then we see a quite large performance difference. So then it can be useful to make use of this warm start that we can get by quite easily defining some labeling functions. All right. So now that we've seen that it works, I will show a bit more how it works. So there's a few different components that are important here. So looking again at this cycle I've introduced, the first step, starting from weak supervision, is to determine which point we need to sample. So yeah, like we saw in the previous talk, there's a lot of different approaches we can take here, but depending on the problem, it's really important to find a good one that really chooses the most informative points so that you can improve the performance the fastest. But our setting is a little bit different, because instead of like a pool of unlabeled data points, we actually have these probabilistic labels for our data sets already, and we want to choose from there which of the points would be useful. So to show how we do this, I'll first note that because of how these labels are created, so they're conditioned on the different weak label values or the different labeling function outputs, we get this distribution where the data points are sort of all in different regions where the labels are all the same, because the labeling function divide up this input space, and within a single region, they all output the same value. So we call these different buckets, and actually our problem is then just choosing a useful bucket to sample from, because the labels are all the same. So if we just choose a useful bucket, we can pick a point from there. And then the key idea that we use to determine a sampling approach is that our goal is that within a bucket, the resulting probabilistic labels that we get reflect as closely as possible the actual true distribution of classes within that bucket. So given that, what we do is we compare these probabilistic labels that we got from the generative model within a given bucket to the distribution that we get if we take only the sampled points. So the sampled point, the points that we've sampled so far as part of our active learning process. So these are the true labels that we've obtained. So for example, for this bucket, the generative model gave probabilistic labels of 0.28, so quite close to 0, while actually in the true labels, they're mostly class 1. So there's quite a big difference. And yeah, we use the idea that if there's still like a big difference between these two distributions, it would be quite useful to sample from this bucket, because we're not really sure if what the generative model said here is accurate. So we quantify that using KL divergence for each of the individual buckets, and just rank them according to that, where we can just pick the bucket with the largest value. So that's, we pick the bucket where the probabilistic labels disagree the most with the true samples that we have. And we compare this approach, which we call MaxKL, the dark blue line, to a few other sampling methods. So margin, where we sample based on uncertainty of the probabilistic as given by the probabilistic labels, or random, where we just sample, pick a random bucket. And what we find in terms of performance is that the other two approaches apparently are more likely to sample less informative points, which makes sense because, for example, the random approach can pick a bucket that where it's already quite certain that it's really one of the classes. So yeah, it doesn't really help to sample from such a bucket. And to see a bit closer what the difference between these approaches is, we also look at the diversity as measured by entropy of the sampled buckets so far. So if the entropy is high, means that we've sampled a lot of different buckets, so explored a lot. If it's low, we sort of are more stuck sampling from the same buckets. And this is often a problem with the margin approach because, quite often we found that you can get stuck sampling from the same area, which doesn't really, then you don't really explore enough to try and improve the model. Okay, so that's the first component. And then after sampling this point that has been chosen according to the strategy, we get the true label. And then the final step is to use the value of this true label to readjust this generative model so that we can actually improve our probabilistic labels. So how we do that by just starting with the objective that we have for the generative model and the same labeling functions, but then also adding a penalty for every point that has been labeled. And this penalty sort of makes sure that the outputs that's from the generative model more closely reflects the true labels that we found. So the penalty, therefore, the penalty measures the difference between this true label and the probabilistic labels that are given by the generative model. So yeah, by adding a penalty for this difference, we make sure that the generative model is nudged towards giving an output that is closer to what we actually have found from the samples that were added by active learning. Yeah, so that's the main idea that helps us actually use these label points to get these better to get a better generative model that combines the labeling functions, and then also better labels and a better discriminative model performance. All right, so to conclude quickly, in many problems, it's difficult to get enough labeled data for your model. So it's a good idea to try and use your expert knowledge as efficiently as possible with techniques like active learning and weak supervision. And we have shown with our method that can be useful to combine these ideas to get better labels and therefore a better predictive performance. And it's especially useful in settings where it's very difficult to label. So the budget is really very limited, because then we've seen that we can get the best performance increase. Okay, so I'm not sure if we have a bit more time for questions.
Cool. Yeah, thanks a lot, Samantha. Of course I know the problem, but what I really like about your presentation and comparing it to if you compare it to the first one, is that you see that if you use if you convert the business knowledge into weak labels, that it really gives a big kickstart to active learning. I think that's really interesting. I'm checking if there are any questions online. I don't see anything. Maybe I'll wait. I do have actually 2 questions for you. Your project at WBAA is over, but if you would have a couple of months more time, this is a new technique. What possibilities do you see to improve this new technique further?
Yeah, there's quite a few things. I guess, so the first issue is that, of course, so for this penalty, we've seen in experiments that it has to be balanced with this loss term. So it has to be scaled by some sort of parameter, but of course it's without labeled data, it's very difficult to tune that. So that's, I think, the first issue that would be interesting to look into further.
Okay, there's another question. And the question is, did you already apply to some specific problems in ING? Or maybe I can broaden that question by, is there a specific problem in ING that you would like to apply this problem to, if you got the chance?
Yeah, no, it hasn't been applied to a problem at ING. Sorry. Yeah, I think there are probably quite a lot of interesting applications, but there's probably a bit more research necessary towards like how this works in different, more complex kind of problems, because it is quite maybe difficult to evaluate. But yeah, like I think quite often where weak supervision is used or active learning only would be interesting.
I think the potential for this technique can be very big. If you have a limited budget to get labels, but you do have some business knowledge that can give inaccurate labels, I think this is a very interesting combination. Okay. Okay, yeah, I think we need to move on. Thanks again, Samantha, for a nice talk. We move on. Jessie, are you taking over?
Yes. Thanks a lot, Samantha. So now it's time for our third talk and our last two speakers. So we have Quentin and Nel, and they will talk about meta-heuristic optimization algorithm to increase automation rate of mortgages and business lending applications. To introduce our two speakers to you. So Quentin is a specialist data scientist in the Belgium data science chapter, who has been focusing on the technical side of the chapter's projects for 5 years now. And we have Nel, and she is an analytics trainee who joined the chapter in October in 2020. So without further ado, welcome Quentin and Nel, and the floor is yours.
Hi. Okay. Hello, everyone.
Hello. Yeah, everything is working perfect. Good afternoon, everyone. So indeed, in the last part of this DS Meetup, Quentin and I will not talk about active learning, but we will present you IRACE, which is actually a meta-heuristic optimization algorithm we are currently employing in the project we are working on. And that project aims to increase automation rate of mortgages and business lending application. And in what follows, we will elaborate on both IRACE and on the project. And so indeed, this is the agenda of today for the next 30 minutes. So we will first explain the use case a little bit in general, and then some specifics for our project, of course. And from there on, we will elaborate on the approach used to tackle the problem presented at the use case. Yeah, we will of course present our solution, but also elaborate on some pros and cons of alternative solutions. And then the algorithm we employed will be discussed. And since the results are confidential, we will just share the general trend there. And of course, there will be some time left for a Q&A, so feel free to drop some questions in the chat. So let's kick off then. And yeah, this next slide. Perfect. This use case revolves around the acceptance and the rejection of applications for mortgages and business loans, as stated before. And the setup for this application acceptance rejection process was done many years ago, and it essentially consisted of a rather classical rule-based decision engine. So it works as follows. When a customer applies for a mortgage or a loan, the decision engine at ING receives the application data, and based on that data, the engine actually verifies how, let's say, how compliant the application is within the decision rules set up by business. So to give you a concrete example, if customer X applies for a mortgage, the engine receives the data, and then, for example, if rule A is not satisfied, then it goes to rule B, and if rule B is satisfied, the mortgage application is automatically accepted. But nevertheless, if a business applies, for example, for a business loan, and rule A is not satisfied, it goes to rule B. Rule B is neither satisfied, then it goes to rule C. And let's imagine rule C tests, for example, some sectors the bank doesn't want to do any business with. If it's satisfied, then the business loan will be automatically declined. So that's a little bit how this decision engine works. And I've been told that the image you see here is one from Porsche, meaning that when this rule-based decision engine was set up, the whole process was very efficient, so it was transparent, and the employees understood the reasoning behind the different rules in the engine. But nevertheless, as time goes by, some problems arose with this kind of setup, and the previously very fast, efficient, clean decision engine became a labyrinth of rules where nobody can really see the forest for the trees. And people who added certain rules, for example, Dave, which you see on the bottom right of this figure, he added the rule in 2010. He does not longer work for ING, and so the new employees don't really understand what is behind the rule. And often, documentation is not really there, or it's not up to date or detailed enough to really understand the update of the rule or the new implementation of the rule. And so, next slide. So this slide actually is a little bit a summary of our use case. So let's say 15 years ago, this rule-based decision engine was developed and automatically accepted, automatically declined, but for our case also very important, can manually decide upon acceptance or rejection of a loan application. And so at that time the results were very satisfactory. Automation rate was quite high, so meaning a lot of applications were automatically decided to reject or accept. And also other KPIs looked quite promising. For example, another relevant KPI is sales. But today, this reason was of course because the rules behind the engine were still relevant for the context then. But today, in 2021, we are left with a complex version of that good engine, and which is actually the result of inserting new rules without really doing sanity checks on the rules which are already in place. And so a lot of rules are no longer relevant in the current context, and as a result, the automation rate dropped a lot, and also other KPIs leave much to be desired today. And so therefore we were asked by business to take a look into how we could tackle this problem. And by we, I actually mean the BADAS team. BADAS is quite a little bit an artificial acronym. It stands for Belgian Advanced Data Science Service. And the goal of the team is to impact and to disrupt the business by delivering projects. The projects are mainly done for different departments within ING. The team is part of the former one-to-one analytics, now digital sales, and now better known as digital sales and customer interaction tribe of ING. And there are currently 7 members. We're working in Belgium. And if you're an ING employee and you're interested in the projects we already worked on or we are working on right now, you can take a look at the link provided on this slide. Okay, so we took a look at this problem, and we mainly identified 2 approaches we could take to tackle the problem. So the first approach would be to just dump the current rule-based decision engine, never take a look at it, and replace it with a machine learning model. The advantages there is that there are quite some cool new and maybe not so new techniques available, which would yield quite good results. But the main disadvantages there are, it's quite difficult to achieve business buy-in because the machine learning model often functions as some type of black box for stakeholders, which is of course not desired. And another point is that if you really set up a new machine learning model, it often takes quite a long time to run through the whole validation process because you're putting a new model there. And it also begs the question, where do you want to put it into production? And this is also a very time-consuming exercise, of course. So then the other approach we identified was the one we went for in the end, which is just to optimize the current rule set, and so bring it back to that very efficient Porsche engine it was back in the time. And the advantage there is that there's still quite some cool techniques available. There are quite a lot of optimization algorithms. The one you choose, of course, depends on your use case. They have certain pros and cons, which is not too surprising. Also, the results are good. And the main advantage there is interpretability, because business stakeholders already know how the rule-based decision engine work. They might not understand all the rules behind it, especially not nowadays. But they understand the functioning of it. A very big advantage is also that it's way easier for validation, because you're just presenting an optimized version of the one that is already in place. So it takes less time. It's not so disrupting for business, and it's already in production, that rule-based decision engine. So you just need to adjust it, and that doesn't take so much time, like max a day or some days. Whereas if you replace it by a new machine learning model, it might easily take some months to put that model into production. And so we went indeed for the last approach, and I will now give the floor to Quentin, who will elaborate on the approach and on arrays.
Yeah, thank you, Nele. So going back to the title, the very lengthy title of the talk, which is about it being a meta-heuristic, etc., etc., I'll go with you a bit more into details in the concept behind iris, behind the optimization algorithm that we chose to use. But first, kind of a top-down view of, in general, how are we applying an optimization algorithm to this business case, to this use case. It doesn't matter too much on this slide yet what exactly does iris do, because it would be the same if you chose to use any other optimization algorithm. Because in the end, what we have is as our input, we have a bunch of data, which is, let's say, a few years of historical data, representing all of those loans, as Nelo explained a bit, all of the loans that come into NG. And we have in that historical data, of course, all the characteristics, all the features that the business rules in the decision engine look at. But because the historical data, we also have what was the historical decision coming out of the decision engine, and was it a good loan to accept, meaning did it in the end result in a sale, and did it in the end result in a default or not for the client. All that is available, of course, because we're looking at historical data. Next to that, we also have, of course, the rules that are in the decision engine, right? And in fact, because we're trying to optimize those rules, we're using meta parameters of the rules. And namely here, in our case, what we are doing is choosing which rules to keep on and which rules to turn off completely. So which rules within the decision engine should be kept active and which ones we are just not going to run anymore throughout the optimization. As well as for some of the rules, maybe not all of them, exactly what the output should be. So as Nero said, right, it's a 3 classes problem that we have at hand. Either automatically accept, reject, or not sure, give the hand to a manual person to take over. So some of the rules we could change the type of output, namely going from a rule that says it looks a bit risky, but I'm not sure, let's go to manual, to changing the output to, okay, it looks a bit risky, let's automatically reject it, which for main KPI of automation makes a lot of sense to skip the manual step. If we're thinking it's going to get rejected anyway manually, might as well reject it in the first place. As well as for a lot of the rules, right? As you can imagine, everyone I think is probably familiar with what business rules look like. A lot of them are just, if the amount is greater than this threshold, then yes. And if that other amount is lesser than the threshold, then no, it should be rejected. Well, those thresholds are also obviously meta parameters, let's say, of that business rules engine. And those are parameters that we can tweak with that optimization algorithm. Of course, what the optimization is doing is trying to optimize something, right? It's optimizing a metric. Namely, in our case, we were optimizing the automation rate that we have behind it. So how many of the applications and how many of the loans end up being automatically accepted and automatically rejected in a way that was positive. So meaning with this backtesting on the historical data, we're interested in accepting the non-defaulting and rejecting the defaulting, for instance, would contribute more to the automation. And next to that, because, of course, if you're just optimizing the automation, why not just turn off all of the rules and just accept everything, right? Then it's 100% automated. Obviously, that's not great. There are other key performance indicators that we want to keep a hold of, and that's why we have an extra layer, let's say, of constraints on top of it all to stop the optimization from going crazy and just turning off everything. Namely, on the other KPIs that we're interested in, and it's a clear credit risk use case. So I don't think it will come as a surprise that we're talking about, the default rate and a sales KPI, let's say. That's what we're interested in. So the general top view approach is we take all of these different aspects, we put it all in this nice optimization algorithm, namely Iris, let it run for a while, does its thing, and then the output is an optimal set of parameters and an optimal set of rules based on those parameters that the algorithm has found as being the optimal one. And then we can validate, checking all of the different KPIs, both the optimization one, so the automation, and all of the other key performance indicators on a validation data set. That's fairly similar to just applying machine learning. The main difference being our output is not necessarily a trained model. Our output is, these are the rules you should keep on in the business decision engine. And then it's a very easy change, as Nelo was explaining just before. It should be a very easy change to essentially redeploy the decision engine as is with less rules into it, right? That's kind of less rules, and some of them tweaked with the threshold is what we're aiming at the end. But let's zoom in into the optimization algorithm. Exactly what is this IRACE thing? So IRACE, it actually stands for iterated racing. It's an open source package, which if you just Google IRACE R, you will find it very easily. But the whole thing, one of the nice aspects of IRACE is that it's very easy to explain. And it's one of the things we have in the conclusion that says, oh, it's very easy to explain even to your business stakeholders exactly how the algorithm works. And that fits perfectly in a half-hour demo like this one to explain conceptually how the algorithm works and how the optimization gets to an optimized set of rules in the end. And the interesting thing is that it's kind of all in the name. It's called IRACE, or iterated racing, and here it's racing like actual, people behind in their cars, Formula One, rally drivers, they're racing like the motorsport. And in fact, the whole algorithm can, to some extent, be explained with an analogy of racing like that. So, right, in the real world, right, motorsport, so obviously I'm more of a IT person, etc. So sport, maybe not my forte, but I'll try to explain it anyway. First in motorsport terms, and then bring it back to the more algorithmic side. But in motorsport of racing, you have different seasons, and you have a winner or multiple winners, the best drivers in one season, but you have multiple seasons, right? The competition is split in seasons, usually one season a year, something like that. And within one season, as I said, you have different drivers, and the different drivers, they're competing against each other to be the best driver that season. It's kind of the idea. But how are they competing? Well, they're racers, they're drivers, pilots, so they're competing with their cars on racetracks. And typically, right, the best one on a racetrack is the one with who did the racing the fastest, right? His time is the smallest. It's kind of optimizing to have the shortest time spent on the track by driving as fast as possible and driving faster than the other drivers. That's kind of the idea. You're getting where you're probably getting where I'm hinting at, that this is all about the optimization aspect. But okay, we'll get to that in a second. But of course, in fact, it's not just about driving as fast as possible, because if you do something crazy on the racetrack, you might get some penalized for it. Let's say you cause a collision and cause an accident. you might have some time added to your clock, even though it's artificial. You did finish it faster than the driver finished the race faster than he really did, because we record the penalized version. But of course, right, the winners of a season is not the guy who wins one race. It's the driver who wins overall across most of the races in the racetracks in the seasons, the pilot that does the best. And on top of that, throughout the season, you might have some driver who drop out of the race because after a few racetracks, they realize, okay, it's completely impossible that I win because I've performed so poorly the first few races, so I'll stop competing, start preparing for next year, for the next season. But typically that means what? And also between seasons, you have people who go like, okay, I did so bad the last few seasons, I'll just drop out and retire from my professional driver motorsport profession. And that means that between seasons, right, to the next season, the top drivers, the one who perform the best, stay on. And then they compete in the next season, and then in the next season, it's kind of all over the same thing again. It's the drivers, they all drive their car on the different racetrack, they get a time, potentially they get some penalties, and then you check the winner of the season is again the one who performed the best across all the different tracks. But of course, because some people dropped out during the season and some people dropped out between the two seasons, you also need to add some newcomers. Otherwise, after a few seasons, you only have two drivers driving. It's no fun anymore to watch, right? So you have this concept of newcomers coming into it, younger driver that try to drive more aggressively or something like that. They come in to try and disrupt who is the champion, the reigning champion of the season. So that's, the clear analogy. This has nothing really scientific behind it. This is all about, rally car drivers. Why am I talking to you about this? Well, if I replace season with iteration, already that should indicate something a bit more algorithmically correct. You don't have seasons, you have different iterations. In the end, a lot of algorithms work with iteration. That should be a term quite known to everyone. And it's kind of the same concept as the season, right? And in our case, for our usage of iRace, the drivers, well, they're not drivers, they're sets of parameters. iRace is a meta-heuristic optimization thing, so it optimizes parameters of something else. And in this case, it's going to be the sets of parameters of a rule-based decision engine. So we're going to have the set of driver. One driver is going to be rule A is off, rule B is off, rule C is on, and the threshold of rule C is this value, etc., etc. And then the second driver is going to be rule A is on, rule B is off, etc. Right, you get a bit the idea. There are different values of the full set of parameters, each of them. And then you evaluate them. You see who is the best performing set of parameters on different instances of your data, basically. Not talking about racetracks anymore, right? You don't throw the parameters on Spa-Francorchamps. Why would they do that? No, you throw it at a subsample of your data. In our case, we were using quarters worth of data. So we would test one set of parameters on all of the loan applications that came in Q3 2015. And then that would be one driver racing on one racetrack. And then the second set of parameters, we test it again on the applications of Q3 2015. That's another driver racing on the same racetrack. And once all of the drivers raced on the first track, then we move on to all the drivers racing on the second track. So test again all of the sets of parameters, but this time on the data of Q4 2015. This is a bit of a similar thing to basically cross-validation in the end, right? It's different split of the data, and you're applying different sets of parameters on different periods to then measure some qualitative KPI. In our case, that was the automation. And then comes in the penalty points. Those are the constraints that we have. So, for instance, one of the constraints was we don't want to increase the default rate That would mean if using a certain set of parameters on one of the quarters of data results in an increase in the default rate, then we would not completely discard that set of parameters, but instead apply a penalty to the, let's say, fitness measurement of how good this particular set of parameters performs on that period. And the same way that the winner of a season is the driver who performs good across all of the racetracks, in this case, the best set of parameters is the one who's going to be, the best sets of parameters are going to be the ones that perform well on all of your slices of data, on all of the periods of data that we put in there. So in this case, it's not the top drivers that stay on, it's the elite configuration, the elite sets of parameters, they stay on until the next iteration. And just like with, the analogy, some of the worst performing ones get discarded throughout the iteration if they perform poorly on the first few quarters of data, and there's no chance they're the best, which translate to statistic tests. Statistically, we can show that the series of data measurement on the different quarters is worse for these than for some of the better sets of parameters. Then we stop testing them on the later quarters. And at the same time, between seasons, we discard a bunch of sets of parameters which are not among the top elite sets of parameters, and we add back for the next iteration some new parameter sets. The main difference here with where it falls off a bit out of the analogy is that the new parameter set are to some extent composed out of pieces taken from the previous elite parameter set, which would be a bit like if rally drivers had children together and then the next season the number 1 and number 2 rally driver get competing against their babies, something like that. It falls off a bit the analogy, but this is the part where it's very similar, in fact, to genetic algorithm, if it's something you're familiar with conceptually, that you create new solutions, new sets of parameters out of the bits of the previous iteration where it worked fine. And then you keep going on like that until you basically converge to one, or to the elite being the same, the elite solutions being the same over multiple iteration. That means you're not improving anymore and you found your optimal sets of parameters. So, of course, this begs the question, why did we choose this particular algorithm and no other optimization algorithm, right? If we go down the approach of using optimization, why this one? Why not nothing else? Well, we think it offers multiple advantages, some of which are completely subjective, right? One, we think it's pretty cool. Obviously, absolutely subjective. And also, it's something that was quite known by at least one of us, namely me, because it's an open source package coming from a university. And guess what? It's the university where I studied. So that's why I already knew about the package and about the algorithm. But on a more objective point of view, the advantages is, at least to us, it's quite easy to use and get going. It's simply just an R package to install. It offers the clients a terminal-based client, a command line interface. It's very much agnostic of whatever you're trying to optimize, because the whole thing is built around the idea that it's optimizing some other black box. Like from the point of view of Iris, from the point of view of the R package, whatever it's optimizing doesn't matter. As long as it can call it through a bash script and that it gets a number out of it, Iris will be happy with it. It will try to optimize that number by changing the parameters it gives to that black box. And also, it's quite easy to get to set it up. There's basically 3.txt file with a few parameters that you need to fill in, and then you're pretty much good to go. And all of that is very well documented, which is always a nice added value and not always the case in all packages found online. Of course, one of the other added value is that this is, the use case we were doing is clearly meta optimization of a set of business rules, and Iris is a meta-optimization heuristic. It is a tool designed to do that. So that's always nice that you can use a tool specifically made for this purpose, right? And in terms of compute time and just being able to run it, it's very easy to set it up so that it's parallelizable because it's just one of the parameters, basically, of Iris itself that you can just say, launch X number of experiments, so X number of testing one set of parameter on one quarter of the data at the same time. And basically at that point, it's up to how much your platform has of capacity. You can go sky high on that number of parallelization. Iris would just launch all of them and then wait for them to finish to get back the fitness score. Now, of course, there is one known downside, is that it's one single objective optimization. So if you really want to optimize multiple objectives, it's not so easy. For us, it was fine because we really wanted to optimize one objective. We had extra constraints, but we weren't aiming to both increase the automation and decrease the default. We were aiming at increase the automation, but without harming the default, for instance. So we weren't doing multiple objective optimization, so that's okay. But obviously, if you are, you might want to look into algorithms that are made to do directly multiple objective optimization. This leads us to the results, which Nele has hinted at before, that they're kind of confidential. As you can imagine, it's credit risk, it's sensitive topics, etc., etc. But overall, it's pretty good. One of the only key feature we were told we can share publicly is that using this, we improve by between 20 to 25% the automation rate. And yeah, that's kind of how much we could say. And in the conclusion, the very final conclusion, what we hope you remember from this is that this is a meta-optimization approach. We hope you think about this next time you're starting a new project. That not everything has to be a machine learning thing. It can also be a meta-optimization, and that can offer similarly good results and make it more decrease time to market. And that specifically the package we've used, Iris, is quite easy to use and easy to explain. And I'm being told we're running out of time. So that's the conclusion of this.
Okay, thanks, Quentin, Manuel, and Nele for the presentation. I didn't know about this algorithm, so I learned about it. We are over time, but I would like to do like one or two questions. There was one, actually there are two online. The one I didn't fully understand. So one question by Aiden. He was asking about the type of rules, business rules. Like he asked, is this about KO rules? I think it's knockout rules or override rules. Does it make?
Yeah, there is different classification of the rules in the engine itself, and indeed the knockout ones, which are basically the more legally obliged rules, those we can't touch. So then they don't go in the optimization. Okay. For instance, a mortgage, one of the knockout rules, which can be publicly shared because everyone knows it, you cannot grant a mortgage to someone less than 18 years old. Right? That's one of the business rules in the engine. That is a knockout rule. If the age of the client is less than 18, he's out.
Right.
Obviously, we can't optimize that. Right. So it's more on all of the other, let's say, more credit risk based rules that we're applying this.
So I also have another question from me actually. So of course it does beg the question: did you try against another algorithm? And I'm thinking specifically about, and of course you want to stay away from complex machine learning algorithms that are hard to explain. But I had this problem in the past myself, and there we did exactly the same thing essentially, but we used a simple decision tree, still very well explainable. I was wondering if you tried against another algorithm.
No, we didn't. in the end, we didn't, right? We obviously planned on trying a bunch of different things, but this was like, okay, this looks promising. This looks like the first thing we want to try.
Mm-hmm.
We did, and the results were absolutely satisfactory for the business stakeholders. And then you're like, okay, then I guess we're going with that. Right? That's a bit.
Okay. Well, if you, I think if you do want to try again something else, just to compare, I mean, at least for me in the past, using a simple decision tree that worked very well explainable. So business still liked it, and that also worked very well.
Yeah,
might be an idea.
Yeah, the main thing as well, right? If you're replacing it with even a simple decision tree, is they have this whole setup with the business rules in production that works in a very specific way, and it's much more complex to replace it by something else than just say drop off those rules and change that threshold, right?
So that's what well, you can do the same thing with a decision tree. You just change the thresholds and decide to keep rules or not. Okay, I think we need to wrap up. Thanks again for the very nice presentation.
Of course.
And I would say if there are more questions still, then let's post them on Slack.
That's a good one. So I think we're here to round up. On behalf of Max and me, I would say thank you everyone for joining, for asking questions, and of course all the speakers. So thank you Anil, Samantha, Quentin, and Nele for joining us and to share a bit more about your use cases. So if you'd like to join us next time, on 11 May, we have a new data engineering meetup coming up. And on 10 June, we have our next data science meetup. So you can find those new meetups on meetup.com, for example, or you'll receive, if you work at ING, agenda invites. So I think that's it from our side. Thanks again from both of us, and hope to see you the next time, and enjoy the rest of your day.